Good morning. As I promised, I'm going to solve for you a few problems which involve viscoelastic models. So this is the first problem. Let's read this together. We have a sample cylindrical specimen of asphalt concrete, which is a highly viscoelastic material. So that's something good to remember. And we have the diameter and the height. And this specimen was subjected to an axial compressive load of 200 pounds for 1 hour. So if you look at this graph here, let's say the beginning there was no load, and then for 1 hour, this is 1 hour or 3600 seconds, we apply a certain level of stress, 200 pounds load, and then we remove it. And everything was done at a temperature of 100 Fahrenheit. And we have the stress versus time and the strain, where we have to add a few values to it. So the values here are 100. The very long time, it approaches 100 microstrain, which is 10 to the power of minus 6, and this value here is 75, and this value here is 30. So the first part of the problem is asking what viscoelastic model would you use to describe this behavior, and then draw the model. Okay. Let's look at the model, and let's look back at the models that we have learned. So if we look at the models that we have learned, for example, this is Kelvin model that we learned last time, when a spring and a dashpot are connected in parallel. And if you look at the creep behavior, let's remind ourselves, we have delayed deformation and delayed but full recovery. So this is Kelvin model. And then we had solid model, where we put in series one spring with Kelvin model, as you can see. And here we have some initial instantaneous deformation, then you have delayed deformation, and if you remove the load, the instantaneous deformation is going to be recovered, and then you have a delayed recovery. Here again you have full recovery. And at the end we learned Berger's model, where we have a Maxwell model and a Kelvin model put in series. So in this case, we do not have full recovery, so the behavior was a little bit more interesting. First you have instantaneous deformation, then delayed deformation, and then and this delayed deformation is a combination of dashpot and also the Kelvin model. And then when you remove the load, the instantaneous elastic deformation recovers. Also, the Kelvin part of the deformation also recovers, but with a delay. What is important is that here, this model predicts permanent deformation. So now that we did this quick review, we look back at the model at the behavior of this material. So first we have some instantaneous deformation, then we have retarded or delayed deformation, and at some point when we unload, we recover that instantaneous elastic deformation, and then we have delayed recovery. So this is delayed recovery, but it fully recovers. So if we think of the models that we learned so far, it looks like this could be Kelvin or solid. It's not Kelvin because in the beginning we have some elastic deformation, so it's actually the solid model. So let's go and draw it. Put the numbers here again. So here is 75, here is 30. So this is a solid model. So make sure that you convince yourself about this, that this is really a solid model. And so we just draw it. We have one spring, and then this is in series with a Kelvin model, which is spring plus a dashpot in parallel. So this is basically the model that we are looking at. So here is the load, and we shouldn't forget to put the model parameters. Kelvin model has 3 parameters. And so we have Kelvin has 2 parameters, but the solid model has 3 because we also have a spring. So we have 3 parameters, and these are E1, E2, and lambda. Okay, so then the next part, it's asking us to calculate these parameters. To do that, it's very, very useful that we add to the strain versus time graph the ordinates that we did in the class, if you remember. So the strain, the total strain here, is basically a combination of the strain from the spring plus the strain from the Kelvin model. So from the spring, it's simple. It is sigma 0 over E1. And the Kelvin model, if you look up your notes, it's a delayed deformation. It looks something like that. Right? Okay. But it's important that we put this on the graph. So if you remember, so the instantaneous deformation is when you apply the load, the spring E1 is going to instantaneously deform. So this instantaneous deformation, I use a different color, is nothing else but sigma 0 over E1. Now, if you wait long enough, if you really wait very long time, basically the strain here will approach sigma 0 over E1 plus sigma 0 over E2, because this exponential term is going to be 0. If you wait very long time, this becomes a very large negative number and the exponential goes towards 0. So we kind of know that this graph here, it approaches to this value sigma 0 over E1 plus sigma 0 over E2. So this is perfect. And we know that this retarded deformation, the rate is kind of it's according to the exponential that we know. Okay, so now we are ready to go. So it is easy to get some of the parameters, a little bit more involved to get the others. So when we ask to calculate the model parameters, means that we have to find E1, E2, and lambda. So to get E1, it's kind of easy. First of all, we have to calculate sigma 0. The load is 200 pounds and the cross section has a diameter of 4 inches, so it's basically the radius is 2 inches. You can write it right like that. So it is 200 4 pi, and if we calculate it, we get something like 15.9 psi. Okay, now that we have it, if you want to calculate the model parameters, which one is the easiest? Well, I think the easiest is to get E1, because we know that this instantaneous deformation in the beginning, the 30 microstrain in the beginning is sigma 0 over E1. Now we also know sigma 0, we just calculated it. So it's easy to get E1. If we do the calculation, we get something like 5.3 times 10 to the 5 psi. This is E1. So now one of the model parameters, we have it. It is 5.3 times 10 to the 5 psi. Great. So let's see if we can get E2. That should be easy too, because we know that the asymptotic curve, it approaches sigma 0 over E1 plus sigma 0 over E2. So to find E2, we say, okay, we know that sigma 0 plus over E1 plus sigma 0 over E2 is equal to 100 microstrain. So at a very, very long time, this is the value it approaches, and we know that. So we already know that sigma 0 over E1 is 30. So from here, sigma 0 over E2 will be 70. And we have sigma 0, so we just substitute and we get, if I haven't made any mistakes, we get something like 2.27 times 10 to the 5 psi. Perfect. So now the only parameter that we are left to find is lambda. So let's look back. We are finding the parameters, which are E1, E2, and lambda. We found E1 from the instantaneous initial deformation. We find E2 from the asymptotic deformation, and then now it's lambda. How do we find lambda? Well, we know that after 1 hour, so this was 1 hour 3600 seconds, we know that the strain is 75. So to find lambda, we need to use this information. We say, okay, we know that epsilon at any time, it can be calculated as sigma 0 over E1 plus sigma 0 over E2 times 1 minus e to the power of E2 lambda t. Okay, now the epsilon at time 3600 seconds, right, is (30) times 10 to the minus 6. This value also, we know it's 70 times 10 to the minus 6, and then we have this term minus E2. Yeah, I can substitute already. Minus E2, which we found is 2.27 times 10 to the 5, and then 3600 over lambda. We know that this is equal to, from the graph here, we know that this is 75 microstrain. Okay, perfect. So now we need to solve for lambda. So if we solve for lambda, so it would be 17 I simplify this a little bit. 75 minus 30 is 45. And then you do the calculations. You are going to get lambda equal to 7.95 times 10 to the 8 psi second. So before in metric system we had like Pascal second, here is like psi second. So now we already have we already could find the three parameters. I don't know, maybe it's useful here to show how we exactly get lambda, because you may not be very familiar with this exponential term. So let me, for those of you who need to see the details, let me add more details here. So we can calculate the numbers this is 8.17 E8, and basically this is equal to 45 over 70, which is 45 over 70, which is 0.64 about. So e to the power of what we had before, which is just a multiplication of the E2 and time that we obtained earlier, is going to be equal to, I'm just moving it to the other side, 1 minus 0.64, which is 0.36. So I'm just moving it here, and now what we need to do is basically to take natural logarithm of so back here again. So here actually I forgot a negative number. So if you want to solve it, so we have to take natural logarithm from both sides. So then this would be equal to negative 1.0217, and then lambda will be over 1.0217, which is the number that we had earlier. Okay, so this is for some of you who may not remember these details from calculus. So let's see, the last part of the problem is actually asking what happens if the material would be tested at lower temperature. which is room temperature. So this original curve was at 100 degrees Fahrenheit. So the question is, what happens if you do the test at 65? So remember what happens to viscosity. Viscosity, if we plot the viscosity versus temperature, if we increase the temperature, viscosity decreases, and if we reduce the temperature, viscosity increases. So we can ignore the effect of temperature on elastic moduli. It has some effect, but it is not very pronounced. So this part doesn't change much. If we lower the temperature, the viscosity formation would be less because you have higher viscosity. And then of course the amount of recovery would not change much, but if you have lower temperature, the rate of delayed recovery will be also slower, meaning that it's going to take longer time for the material to recover. Everything becomes slower. The flow becomes slower because the viscosity will be higher. So it's important that you are very comfortable with the effect of temperature and viscosity, and you can analyze how it would change the model response. Okay, so this was the first problem that I wanted to solve for you. We have all the three model parameters. The instantaneous we got from the elastic deformation in the beginning. From the asymptotic deformation we got the second elastic modulus, and then just looking at the strain at one point, we could also get the viscosity. So yeah, I also showed you how to calculate it with a little bit more details here. Okay, so now we are ready to look at the second problem. The second problem concerns a polymer rod, and the cross section is a square. Each side is 5 millimeter, and the original length, so the rod length before loading, it's like L0, is 500 millimeters. So we apply a tensile force and we measure how it changes over time. First, when we apply it, instantaneously the load is stretched to 508 millimeter. So this is when we say instantaneously, we have to immediately think elastic, right? And so if you want to calculate the elastic strain, the elastic strain would be basically elastic or instantaneous would be basically 508 minus the original length over the original length. So we can easily calculate that. So this is 0.016, and then we hold the load. So we are keeping the load constant, right? We are not changing the load. So this is constant. And so we are thinking about a creep problem. So after 24 and 48 hours, we have calculated also the length. So at 24 hours, the rod is 550 millimeter. So again, minus the original length over the original length. So all we are doing is really looking at delta L over L0. So this is 0.1, and we know that at 48 hours it's a little bit longer. For 570 minus 500 over 500, and this is about 0.40. And then the load is removed. So then we are looking at to see how the recovery process is going to develop. Now we had a load, 500 Newton, we kept it constant, so we are looking at a creep deformation, and then now we remove the load. And if we wait a very long time, we still see that the rod doesn't go back to its original length. So the permanent strain, the permanent deformation, permanent strain is 525 minus 500 over 500. Now, here the hint is given that this is a Berger's model, but we could have guessed it too, because we have instantaneous deformation, and also we have permanent deformation. And we also see that the deformation is time dependent. So even if we didn't know, we could kind of guess which model it is. So we want to find the model parameters again. Let's remind ourselves, or try to draw things a little bit and remind ourselves about Berger's model. So Berger's model, if you recall, it was a Maxwell model, which is like a dashpot and a spring in series, and then you add to that basically a Kelvin model. So this is E2 and Lambda 2, and then you apply some load, which is in this case 500 newtons. And it is constant, so it is free. And if you recall, the strain versus time formula is of course a combination of the Maxwell and the Kelvin summed up. If we want to think about model parameters, we have 4 model parameters. We have 4, and it is E1, lambda 1, E2, lambda 2. Great. So if we draw the strain versus time curve, as you can see here, it's important to kind of think about the things we heard. So here we have the instantaneous or elastic deformation. Then at 24 hour and 48 hours, we kind of calculated the strain. We have 0.1 and 0.14. So maybe for instantaneous deformation we also put the number 0.016, and the recovery is going to be equal to the elastic deformation. It's 0.016, and then we are going to have, this is the instantaneous recovery, and then we have delayed recovery. And of course at the end we have some permanent strain, which we calculated to be 0.05. So we want to again find out what are the model parameters here. So the model parameters are E1, lambda 1, E2, and lambda 2. Let's see. If you want to find E1, just like before, we should look at instantaneous deformation or strain. So we know that the instantaneous deformation is 0.016. This is basically, if you read the problem statement, is 508 minus 500 over 500. So this is pretty much should be equal to sigma 0 over E1. So it's useful first to calculate sigma 0. Sigma 0 is of course is force divided by area. The force is 500 newtons and the cross section is squared, 5 by 5, so you have 25 millimeter squared, and the stress turns out to be 20 megapascals. So this is great. So to find E1, so we can easily say, okay, sigma 0 over E1 is 0.016. I know what sigma 0 is 20. So this gives us E1 12 50 megapascals. So now we have E1. One parameter is found. Great. Now, which other parameter can we find now? So, this is a little bit complicated than the previous example. One parameter that we can find is actually lambda 1. How? We should remember that the elastic deformation due to the spring in the Maxwell model and due to the Kelvin model, they are going to recover. So the only part which doesn't recover is actually the viscous deformation due to the dash spot in Maxwell model. So if we remember that, then it becomes somewhat easier. So to find lambda 1, we remind ourselves that the permanent strain is due to dash spot lambda 1, because everything else is recovered either instantaneously or delayed. So if we recognize that, then we can obtain lambda 1. So the permanent strain is 0.05. This should be equal to sigma 0 lambda 1 and the duration of loading T0. We know that sigma 0 is 20, T0 is, the total is 48 hours, so we turn it into second over lambda 1 is going to be 0.05. So if we do the calculations, then we get lambda 1 6.91 times 10 to the power of 7 megapascal second. Okay, now to find E2 and lambda 2, basically we have to use the other information. In particular, we have to use the information that we have about the strain at 24 hours and after 48 hours. We recognize that the delayed recovery is basically due the Kelvin model. So if we write, so to find E2 and lambda 2. So we recognize that we have the strain at 24 hours, it is 0.1, and then we have the strain at 48 hours, which is 0.14. So what we could do is just substitute in the equation. So if the strain at 24 hours is 0.1, we can just substitute in the equation for a strain. So 0.1 is equal to the initial instantaneous strain 0.016 plus the dashpot, which is 20 times 24, 3600, and we already know how much is the lambda 1, so that makes things easier. And then finally the last term, which is sigma 0 over E2 1 minus E minus E2 lambda 2, and this is 24. So this is also 20. This we know too. Okay, so we can also do that for 48 hours. So it's 0.14. So here we have 0.016, and this we know it's the permanent strain, which is 0.05, and then we have again 20 over E2, and this time minus E2 lambda 48 times 3600. And if we do the calculations, this quantity will be about 0.025. So we can simplify these two equations as follows. So from epsilon at 24 hours, we obtain basically 20 over E2 1 minus E2 over lambda 24 3600 and this is 0.1 minus 0.016 minus 0.0025, which is going to be 0.059. Okay, and then from the epsilon at 48 hours, we obtain a slightly different equation. And it is 0.14 minus 0.016 minus 0.005 this time, which turns out to be 0.074. So we have two unknowns, E2 and lambda, and we have two equations. So we can obtain we can obtain the values. So if we do the calculations, E2 turned out to be around 253 megapascal, and Lambda 2 turns out to be 1.6 times 10 to the power of 7 megapascal second. So basically we have all the parameters that we were looking for, we have them. So again, when we look for parameters, this is a very practical example, because typically what we do in the lab, we measure the response and then we try to fit a material model to the data and to obtain the parameters. We have to kind of remind ourselves which part is instantaneous, which part doesn't recover, which part will recover later. For example, an alternative approach here would have been that we would recognize that the delayed recovery, so we would recognize that the delayed recovery is basically it's related to Kelvin model. So if we did that just by looking at the graph, we would basically see that the delayed recovery would be 0.14 minus 0.0016 minus 0.005, which is the permanent strain. So this is, we would see immediately that this is 0.0074, and we knew that this all is caused basically by Kelvin model, which won't give us a different equation, but it's kind of maybe easier and more understandable. So it is just the same equation as when we substitute for strain at 48 hours. Okay, so this is about the second example. You have an example very similar to these two examples I just solved for you in your homework. It's actually easier than and this one. So I hope that this helps you to do your homework problem. And now let's not forget why we were learning these models. So if you remember, I talked to you about falling water, building, and the creep problem. So creep is an important problem. It's a time-dependent strain, which happens when you actually are not changing the stress. So let's look at a typical creep behavior again. First, we have this instantaneous strain, and then you have this primary, and then you have this secondary, which is sometimes also called steady state, because it's linear. And if the load is there for a long time, then you enter a tertiary phase, where it actually, the pace picks up and then it eventually leads to failure, rupture due to creep. So it is basically creep failure. I hope that you recognize that at least up to the point where the material is close to failure. For example, Berger's model is actually a pretty good model. If you just compare the response of the Berger model to here to what you will see in the lab, you see that basically we can very nicely characterize this behavior of Berger model. So there is a parameter that sometimes people measure in the lab, and that's called the creep rate, or a steady state creep rate, and it's nothing else but basically the slope of this secondary phase. So in one of the quiz homework problems, I've asked you to actually obtain that. So that means just look to see what the rate of strain is during the secondary phase of creep. So basically we were able to learn about viscoelastic models, which helps us describe this creep behavior. So we achieved what we set out to do. It's also important to recognize that because creep is a viscoelastic behavior, temperature has a very important effect on creep strain. So we have done many examples about changing the strain, the temperature, and you can see that if you change the temperature, so basically this slope is going to increase, so you are going to get more and more deformation, and the rupture, the creep failure, will happen sooner because you reach to a higher level of strain sooner. You had seen this before, but I thought it's good to kind of bring everything together. Now, to wrap everything up, this actually wraps up the whole module 1. Let's go back and remember what we learned. We learned about viscosity. We learned that viscosity is the characteristic of viscous materials, and they are different from elastic materials in the sense that the deformation is time dependent. In viscous materials it's instantaneous, in elastic materials, and in terms of recovery, elastic materials we have full recovery, and viscous materials, if it is fully viscous, no recovery at all. We learned about Newton's law, and we learned that in Newtonian fluids we have the stress and strain rate are proportional. So elastic materials, stress and strain are proportional. In Newtonian materials we have stress and strain rate proportional. This can be normal stress or it can be shear stress, and this proportionality, we call this viscosity. Temperature reduces viscosity. We learned that if you increase the temperature, material becomes less viscous, it flows easier, because viscosity, remember, it's the resistance to flow. And then everything became more interesting. We learned that typical materials are neither fully elastic or fully viscous. They are typically behaving viscoelastic, means that they are partially elastic, partially viscous. That means that you have partial time dependence behavior and partial recovery. And we learned that if we keep the stress constant, the strain is going to increase over time. This we call creep. If we keep the strain constant, the material is going to relax itself. So you're going to have decreasing stress over time. This we call relaxation. And then we learned that we have a spring and a dashpot, which are material models for elastic and fully viscous materials, and like a Lego, we put them together in different configurations and we make other models, and our goal is to describe the behavior that we see in the lab, because we have to have a means to describe the material behavior, and we saw that Hooke's law is no good anymore. These behaviors are time dependent, and what we knew before, it's not going to help us. So we learned about Maxwell model, where the spring and the dashpot are in series. We have two model parameters. We have Kelvin model, where the two are in parallel, and we have solid, which is just adding a spring in series to a Kelvin model. And now we have three model parameters. So here we had 2, here we had 2, and here we have 3. And then finally we found a very good model which we saw was actually quite realistic, and this is Berger's model, and it has 4 materials parameters. And we learned the response, we learned the creep response of everything, we looked at the relaxation response of Maxwell model too, and we learned how to get the parameters. So calculating the parameters we learned in the examples. So, and finally, if we look at the buzzwords and technical terms we learned in this module, we learned about viscosity, about viscoelasticity, about creep, relaxation. Now we know what a materials model is, and also we learned about activation energy, and we talked about that in the context of the dependence of viscosity on temperature. So if you forgot, I encourage you to go back and review. So this concludes this lecture. Remember that the homework is due on Friday, and also there will be a quiz on Friday. Okay, bye.